Hi. In this work, we investigate the utility of Koopman operator theory in learning dexterous manipulation skills. Why would we want to use Koopman operator theory for dexterous manipulation? First, dexterous manipulation skills are driven by complex underlying dynamics, and the Koopman operator is a simple but powerful control theoretic tool which can approximate such complex nonlinear dynamics as linear systems in higher dimensional spaces. Second, Koopman operators can be learned analytically without relying on gradient descent. So, compared to existing learning algorithms, we can significantly lower computational burden and remove sensitivity to parameter initialization. Third, given that we can learn a linear dynamical system, we can leverage a variety of control theoretic tools, such as Lyapunov and contraction analyses, to inspect the learned policy. We contribute a novel imitation learning framework called Codex, short for Koopman operator-based dexterous manipulation. From a set of demonstrations, Codex extracts the complex and interconnected dynamics that underlie the desired motion of both the robot and the object. Codex represents these dynamics as a linear dynamical system in a higher dimensional space. The Koopman operator K is a matrix that defines the lifted linear dynamics, and Codex learns this operator analytically. We also learn an inverse dynamics controller to generate control commands that can track the robot reference trajectory generated by learned reference dynamics. We evaluated the utility of Koopman operator theory on 4 dexterous manipulation tasks that are commonly used in the literature. They are tool use, door opening, object relocation, and in-hand reorientation. We found that Codex is able to learn to successfully perform all 4 tasks despite its simplicity, suggesting that Koopman operator theory can indeed be useful for dexterous manipulation. We carried out rigorous quantitative evaluations of Codex and compared it to 2 standard policy architectures and 2 state-of-the-art imitation learning algorithms for manipulation. We evaluated all baselines across 5 random seeds. Across all tasks, we find that Codex can perform comparably to these baselines, and even outperform them in some cases. Most importantly, Codex is able to do so consistently and at an order of magnitude lower computational cost. We also evaluated the sample efficiency of Codex and compared it to the baselines. We find that Codex almost consistently achieves the lowest imitation error and the highest task success rate with the fewest number of demonstrations. These observations suggest that Codex tends to be more sample efficient than the baselines, thanks to Koopman operator's ability to capture nonlinear dynamics. The only exception to this trend is the object relocation task. We suspect this is because Codex might need more demonstrations to capture the high variance in the hand-based trajectories as the hand moves across a large task space. We also find that Codex's training time increases at a significantly lower rate compared to the baselines as we increase the number of demonstrations, suggesting that Codex scales much better with demonstrations than the baselines. Lastly, we believe we have barely scratched the surface with respect to the potential of Koopman operator theory for dexterous manipulation. There are numerous avenues for improvement in future research. First, when trained on 200 demonstrations and tested on 200 out-of-distribution samples, we see that Codex has a limited capacity for out-of-distribution generalization in its current form. Future work can investigate if this can be improved by swapping the polynomial lifting functions that we use with learned lifting functions. Second, we have not deployed Codex on physical hardware. Doing so will reveal how these advantages translate to physical systems. Third, we can use the same ideas in this work to learn system dynamics from data collected via self-play, and then use the learned model to enable model-based reinforcement learning. Fourth, it was recently discovered that there is a strong connection between Koopman operator theory and contraction analysis. This relationship can be leveraged to derive theoretical guarantees. Thank you for your time and efforts in reviewing our paper.